Acids and bases, high level 4, pH curves, indicators. The essential idea. pH curves can be investigated experimentally, but are mathematically determined by the dissociation constants of the acid and base. An indicator with an appropriate endpoint can be used to determine the equivalence point of the reaction. Nature of science. Increased power of instrumentation and advances in available techniques. Development in pH meter technology has allowed for more reliable and ready measurements of pH. So what are indicators? Well, indicators are weak acids or bases where the undissociated and dissociated forms have different colours. For example, HIN, the molecule, dissociates into the hydrogen ion, and the indicator ion would have different colours. Let's look at an example of methyl red. On the left there, the molecule methyl red, where the carboxylic acid portion is intact, is yellow, and that's in equilibrium with the hydrogen ion and the indicator ion, where you've lost the hydrogen here, and that would be red. And of course it depends on the amount of H+, whether the equilibrium will be this side or this side, whether it be yellow or red. So adding an acid or a base will change the equilibrium. It'll change the concentration of H+. Le Chatelier's principle states that the equilibrium will shift to minimize the effects of the stress. So if we add an acid, then we're increasing the concentration of hydrogen ions. The equilibrium will shift to the left to to minimize the stress of adding more H+. It'll shift this way. And so you get an increased concentration of the molecule of the indicator and a decrease in the concentration of the ion. So colour 1, this side of the equilibrium, will dominate. If we add a base, the concentration of hydrogen ions will decrease, the equilibrium will shift to the right, we'll move over this way, so the OH minus will be grabbing this, taking it out of solution. This will then move to the right to counter that stress. And the increase in the indicator ion and decrease in the indicator molecule will mean the colour 2 dominates. There's a bunch of different indicators. Let's have a look at this table. If we've got brom chrysol green, we've got a transition range between 3.8 and 5.4. When the pH is lower than the pKa, it's in its acid form and the molecule form, you're going to get yellow. Colour in bases, when the pH is greater than pKa, it'll be in the indicator form, which is blue. For methyl red, the transition range is between 4.4 and 6.2. When pH is lower than pKa, it's going to be red. When pH is larger than pK, in the base form, it's going to be yellow. Bromethyl blue. Colour in the acid, when the pH is less than a pKa, it's going to be yellow. The colour in a base, when the indicator form is in excess, and the pH is greater than a pKa, it's going to be blue. And phenolphthalein goes from colourless in acid to pink stroke magenta in a base. Okay, so the acid dissociation constant for these indicators here, we've got the ions obviously on the top as normal, we've got the molecule on the bottom, concentration, concentration, concentration. When the concentration of the molecule is identical to the concentration of the indicator ion, then the indicator is in the middle of its transition range. And therefore, the dissociation constant will equal the concentration of the hydrogen ion, which kind of makes sense because the indicator ion, concentration of this will cancel out to be 1. And therefore, if Ka equals the concentration of H+, we know the negative log of Ka is pK, the negative log of H+, pH, and so pK equals pH. The pK value of an indicator is sometimes called the endpoint of the indicator. Let's look at table 22. This is from the chemistry data booklet. It gives you information about indicators. You can see it gives us the name of the indicator, gives us the pKa value, the pH range, and you can see that the pKa normally falls somewhere within the middle of it, and it gives us the colour in acidic conditions or the alkali conditions, where red would be on the 3.1 side in this case, yellow would be on the alkali side of the range. Here, yellow would be at 3.8 side, blue would be 5.4, and it would, like, the yellow would gradually turn to blue, or the blue would gradually turn to yellow. So somewhere in the middle, you'd have a kind of mixture of blue and yellow. With that in mind, what is the colour of methyl orange in a solution with a pH of 5.2? Well, methyl orange is here. A pH of 5.2 is on the alkali side of its range, and so it's going to be, the alkali colour is yellow. Solution Z, or Z, has a pH of 5.8. Determine its colour in phenolphthalein. 5.8 is below its pH range, so it's going to be acidic, and the acidic colour is colourless. Methyl orange, 5.8 is above the range, more alkali, so it's going to be yellow. Bromophenol blue, 3 to 4.6, so the pH is going to be above that, more alkali, so it's going to register alkali, it's going to show a blue colour. Two unknown solutions are tested with a variety of indicators. Give the most precise pH possible for each solution based on these results. Solution K. If you look back at the table and look at all of these different colours here, you can see the colourless yellow, blue, yellow are all just fine. They are all present here. However, orange for methyl red isn't. You can see methyl red is red or yellow. But we do know that a mixture of red and yellow gives us orange. And so a shortcut here would be, we know it must be almost in the middle of 4.4 and 6.2, which is of course about 5.1. So the pH would be roughly 5.1. For solution Q, phenolphthalein is colourless. So we know it's going to be on the acid side of its pH range, so it's going to be below 8.3. So let's go to the very next one, phenol red. Let's see if it's below phenol red as well. Phenol red, it's red. So, so it's alkali. It'll be on the alkali side, so it's going to be on this side. So it'll be on this side phenolphthalein and this side phenol red, and so a good guess or estimation would be 8.3. Splendid.